two sample t-inference on the difference of means, the parameter, difference of two population means, the statistic is the difference of two sample means. If we recall that the standard error of sample means is this, then the variance would be s squared over n. And that's why the formula for the standard error of the difference of two means would be the sum of the variances, and then you take the square root, because once again we're dealing with the joint distribution if we're looking at the difference of sample means. So let's look at a problem. Let's suppose we're testing brake A versus brake B on automobiles, and we see the data. We see that these were the stopping distances for cars with brake A and the stopping distances in meters for cars with brake B. And the first thing we want to ask ourselves when we come across this data would be, are the two samples independent of each other? Now we would prefer to have done this experiment as a crossover experiment where these were the same cars. The same car used brake A, and we looked at how long it took it to stop the car, and then that same car would be fitted with brake B and we'd stop the car. So if that's the case, then these two sample sets are dependent, and we would take the difference of all the stopping distances and do a paired t-test using the procedures with just a regular old t-test. But suppose we didn't do it that way. We did a completely randomized design, and we ended up with certain cars were fitted with brake A, and then a different set of cars were fitted with brake B, and these were the stopping distances at the same speeds using the two different brake types. By the way, Max, this one's for you, man, because you love my puns more than anyone. Suppose we did this test at night, and so we had to have the headlights on, of course, and what if just prior to stopping there was a deer caught in the headlights and boom, it got hit? And what if that deer had antlers? Then I would estimate that the car would stop about here, but that the buck stops there. It's awesome. You could also use this joke if it was a man that you hit and he had a wallet, so you know the buck stops there also. But anyways, these let's assume that these two samples are independent and that we're going to run either a test to see if one brake is better than the other, or we're going to do a confidence interval to estimate the stopping distances, the mean stopping distances between the two brakes. So if we put our data into two lists in the calculator, we could get these statistics right here. And if we ran a confidence interval on the test, the calculator will give us the degrees of freedom. So let's suppose that's what we're doing. We want a confidence interval. We recognize that the parameter that we're estimating is going to be the difference between brake A and brake B's mean stopping distances. So if that's our parameter, this is our statistic, and our standard deviation is a joint distribution standard deviation we can find on the formula page. So we would plug in all the information that we got off the calculator. We need to find our critical t-score. We prefer in class to use our calculators to go use the inverse t function and say that we want to trap 5% on a tail if we're doing a 90% t interval. So we would trap 5% on the tail with these degrees of freedom, and we would get this t-score. You can always also use the table. Different teachers have different preferences, but this would be our critical t-score. Toss it there, and that's going to be how we get our confidence interval for the mean stopping distance. And we would say that we're 90% confident that the difference between the mean stopping distance, brake A versus brake B, for cars traveling at the same speed would be between whatever those two values are. If instead we're going to do a hypothesis test, then the wording is often this: is this evidence that type A brakes have a shorter mean braking distance than type B brakes? And in this case, we would do a write-up. I have my kids do a 5-step write-up. AP talks about a 4. It's the same idea. Basically, we name the test, or the test would be a 2-sample t-test that on the claim that the mean stopping distance for type A brakes is less than the mean stopping distance for type B brakes. At some point at the beginning or in your conclusion, you want to make sure that you clearly delineate what those means are, what those things stand for. The null would be that the two breaking distances, the mean breaking distances, are equal. The alternative is what the claim was, that the mean for A is less than B. Assumptions, that the data came from a random sample. We addressed that. Let's say, yep, we were told this was a random sample. We need the two samples to be independent of each other, mutually exclusive. We don't know the population standard deviations. That's why we're using T. And then if we know we have sample sizes of 9 in both cases for both breaks, so that the sum of those is less than 30, we're not told if the populations were normal to begin with. So what we're going to do is maybe make a dot plot or a stem plot of both sets of data. So this is break A, stopping distances. These are break B, stopping distances. And we just look at those and we say, you know what, there's no reason to doubt that they're symmetric or the populations they came from could be normal. And like I instruct my students, after all, the T distribution is a robust, the T-test is a robust test, can overcome violations of normality. So the sum of the two sample sizes is over 15. We're in good shape. There's no concerns as far as meeting the requirements, the conditions for doing a T-test on this, two-sample T-test. To continue with the work, we can go to the calculator and type in the numbers and let it do the work. But again, the formula sheet, the statistic minus the parameter, the null says no difference, so we get the difference in our sample means. It's a joint distribution. The sum of the variances, or the square root of the sums of the variances, would be our standard deviation. From the calculator, we could get our t-score. We're a little less than 1 standard error away from a difference of 0. In the sampling distribution, we would assume a difference of 0. The difference of our two sample means is down here, about 1 standard error to the left of that. So it's not a very unusual result. We can see the p-value, the probability of type 1 error is pretty high. So we're not going to risk going with the alternative. We should write down degrees of freedom. And in the end, we make our conclusion. We say because the probability of type 1 error is more than 5%, or whatever we chose as a significance level, we fail to reject the null. And like we've talked about before, we should oftentimes then say what the evidence suggests in terms of the alternative. The alternative suggested that means for break A would be less than the mean stopping distance for B. But because we failed to reject the null, then the evidence fails to suggest that the alternative is true. It fails to suggest that the mean breaking distance for type A is less than the mean breaking distance for type B. We pretty much never worry about pooling with two sample means like we do with the two proportion z-test. The two proportion z-test, we pool all the time because the null states that the two proportions are equal, which by default means that their standard deviations and variances are equal because their standard deviation and variance formulas involve the proportions. In sample means, we rarely can assume that the two populations have equal standard deviations and equal variances, so we don't really worry about it much. We pretty much never pool in two sample t-tests. If they do make a big deal of, hey, the population variances are assumed to be equal, then we'll go ahead and pool, but we don't really end up doing that in life very often, and the AP tests almost never ask you to do that. So stick to the solid understanding of the components of the write-up and the fact that you have a joint distribution with the square root of the sums of the variances as your standard error, and life should be good. Good luck.